Alright, so let's take a look at some electron configurations of elements and ions. So here's the periodic table. I already pre-numbered it. The S block, D block, P block, and F block. So let's write the complete electron configuration for magnesium. Notice magnesium is atomic number 12. So it's going to be 1s2, 2s2, 2p6, 3s. Let's see, it's 3s block, second one over, 3s2. 2 plus 2 plus 6 plus 2, that is 12 electrons. That's the complete electron configuration for magnesium. Now magnesium ions, magnesium forms a positive 2 charge. So notice that since it's a positive charge, it means it had to lose 2 electrons. If I'm going to take electrons away, where do I take them from? It turns out for cations here, the electrons are going to come from the valence electrons. And how many valence electrons does magnesium have? It is 1, 2. 2 valence electrons. They always come from the valence electrons, which corresponds to the highest value for n. In this case, it's 3s. So I'm going to take 2 electrons away from the 3s orbital. They're going to go away to now give me the electron configuration for magnesium cation, which is 1s2, 2s2, 2p6. So magnesium plus 2 has the same electron configuration as neon. Neon also ends in 2p6. The difference, however, is that magnesium cation has 12 protons, neon element has 10 protons, and therefore I expect magnesium ions, Mg2+, to be smaller than Ne because of the extra positive charge of the nucleus. Generally speaking, cations are always going to be smaller. In this case, if the 2 elements have the same number of electrons, the one with the more protons are going to be smaller. And clearly, Mg plus 2 is going to be smaller in size than Mg neutral, again because of the extra positive charge. Let's try another element for an ion. Let's consider, for example, sulfur. Sulfur and S negative 2. Sulfur's electron configuration ends in 3p4. And ends in 3p4. So let's write the complete configuration for sulfur. 1s2, 2s2, 2p6, 3s2, and 3p4. Alright, so sulfur is right here, number 16. So it's 1s2, 2s2, 2p6 takes it through neon, 3s2 takes it through magnesium, 3p4 gives me my sulfur. 3p4. If you notice, sulfur now has got how many valence electrons? Sulfur has a total of 6 valence electrons. So for valence electrons, we're going to count left to right. So 1, 2, skip the middle, 3, 4, 5, 6. 6 valence electrons. It wants to look like a noble gas, so it wants to fill up this p orbital, fill up all the p orbitals here. So sulfur wants to get to a 3p6 configuration. It wants to basically fill in the vacancies in its orbitals. So sulfur, because it's in group 6 of the periodic table, it wants to gain 2 more electrons. So let's see, it wants to plus 2 electrons, so it wants to gain 2 more. That gives me 1s2, 2s2, 2p6, 3s2, and finally 3p6. That ends up being the electron configuration for sulfide, S negative 2. Since S negative 2 has got more electrons than protons, it is larger than this S. S negative 2 is larger in size than sulfur neutral. Anions are always larger than the parent atom at which they come from, compared to cations, which are always smaller than the parent atom which they came from. So Mg2 plus is going to be smaller than Mg neutral, where S negative 2 is larger than S neutral. That's how we're going to handle our simple elements. Now, what about transition elements? Notice iron. Iron atomic number 26. It's going to end with 3d6. So iron's going to end in 3d6. So I have Fe, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now you might recall from introductory chemistry and earlier this semester that iron can have more than one charge. Iron can be positive 2, and iron can be positive 3. Again, when it comes to cations, we're going to take electrons away from the highest value of n first. So the highest value here is going to be the 4s. So the iron plus 2 comes from taking 2 electrons away from iron, taking them away from the 4s energy level. So that gives us 1s2, 2s2, 2p6, 3s2, 3p6, followed by 3d6. That is electron configuration for iron positive 2. When it comes to iron positive 3, now I have to determine where to take the extra electron from. Clearly, I'm going to take 2 from the 4s, and now I need to take away 1 more. Well, let's take a look at this d orbital looks like. I have 5 of them. So it's 1, 2, 3, 4, 5. If I put these 6 electrons inside, it's up, 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 up. You always fill up first, then down. I got 1 more. So if you notice, if I were to take 1 electron away from the d orbitals here, if I take away this guy, what happens is that I'll be left over with 5 orbitals with 1 electron in each of them, all pointing with the same spin. That gives extra stability. Recall that these electrons are all negative charge. They're all in separate orbitals. They're trying to repel each other as much as possible. So by taking 1 electron away here, I now can maximize my repulsion, gaining maximum stability of these electrons. So I'm going to take 1 electron away from the d block. So with electrons for iron plus 3s will end up being as 1s2, 2s2, 2p6, 3s2, 3p6, and followed by 3d5. So it turns out even having halfway filled orbitals is more stable than having an orbital with possibly, with an extra electron inside. That also applied to the p's as well. We're going to find that having, for example, in the p block, we're going to talk about periodic trends later in this chapter, you'll find situations where having halfway filled p orbitals that is more stable than having situations where we have something paired. Okay, so we're going to find special stability in these cases where halfway filled. Likewise here as well. And this is why the transition metals can form multiple charges. We're always take electrons away from the s sublevel first, followed by the number of d electrons in order to get the ion of interest.